All right, so that's the first law of motion. Let's shift gears. Let's talk about the second law of motion. This is known as the law of acceleration. And in words, it's when an object is acted on by one or more outside forces, the total force is equal to the mass times the acceleration. In equation form, last bullet on the screen. F equals ma, but we got that goofy thing in front of the F. It looks like somebody knocked the letter M over. Thunk. Just kind of thunk. Anybody recognize that letter?
Sigma.
I'm sorry, George, what?
Is it Sigma?
Yeah, it's capital Sigma. And it stands for summation. So it's saying, what that last bullet says, the sum of all the forces. Okay, so sigma S, it's like our capital letter S. Sigma F, so sum of the forces equals ma, mass times acceleration. Tony, do you guys use the Cyrillic alphabet? Oh, we lost Tony. Oh man. Or did we lose Tony? No, Tony's out there. Tony, do you guys use the Cyrillic alphabet?
What?
Where you are, do you use the Cyrillic alphabet?
Yes.
So do you have a letter like sigma in the Cyrillic? Because I know the Greek and Cyrillic is close in some places.
Yeah, but not exactly. No, we have a
Okay.
Z, but it's like a three, like the number three.
Okay, so it's kind of pointing the other way from this one.
Yeah, kind of that.
Okay. All right. Anyway, I just thanks. Yeah, thanks for part of it. Yeah, I love learning. I get to learn from some of the students sometimes too. So, all right. So that's like our capital letter S that means summation. So sum of the forces equals the mass times the acceleration. And in my brain, it's easier for my brain to remember that equation than all those words. Okay. And so that's Mr. Newton's second law. And so the picture that I've got on the screen here, okay, that box has mass measured in kilograms in the metric system, okay? The young man is putting a force on that box. The force, if he's the only force acting on it, the force that he is putting on that box, the amount of force he's, yanking on that box is going to be equal to the mass times its acceleration. And even closer to home, we experience this every day. Guess what? Our weight is a force. It's our mass times the acceleration due to gravity. And since it's important to pay attention to units, so it'll save you bacon, let's talk about units. Units for mass in the metric system. I've kind of already hinted it's kilograms. Anybody know what the units for mass in the U.S. customary system is? It's the slug. Yes, Tony, it's the slug. Here in the U.S., the units for mass is slugs. Where slugs came from, I have no idea. And George, have you heard of these yet? Because last week you were telling me about the unit systems. You've got a weird blend of metric and U.S. customary down there in Panama.
Yeah, we got a hybrid, but we don't have slugs and we don't have stone, so we don't go that far.
What about firkins? Do you have firkins?
No.
'Cause there's a whole unit system called furlong fortnight firkin, FFF unit system. Anyway, sorry. So I know Tony, you guys are metric. So George, you've got a blend of metric. Joe, you're here, so you got U.S. customary. Meg, you're here, so you got U.S. I'm in the U.S., so I got U.S. customary. And since I still have students here in the U.S., I tend to kind of work through both unit systems just so everybody's comfortable with them. All right, so if we've got mass in either kilograms or slugs, and we got acceleration in the metric system, remember acceleration is meters per second squared. In the metric or U.S. customary, it's going to be feet per second squared, right? So that means that mass times A. Acceleration is force. So the units on force, Megan, you said it already. What's the unit for force in metric system?
The Newton.
The Newton, thank you. And in U.S. customary, it's what we call the pound. All right. So Tony's probably got a good feel for what the Newton is. George, you might, but here's a pound. 1 pound is about a little more than 4 newtons. Or you can flip it over. 1 newton is about a quarter pound. So Joseph, next time you're running through the drive-thru, see if you can order a Newton burger, okay? So that little patty of supposed beef is roughly 1 newton. It's about 1 newton. Tony, I'm guessing you got McDonald's there, right? Yeah, they're kind of everywhere. Them and Coca-Cola. They're everywhere. They're everywhere. All righty. To help bring this
Diabetes.
home. Yeah, go ahead, George.
I was gonna say, and diabetes.
And diabetes, yes. And high cholesterol and, All right. All right. This is an example out of your textbook, kind of bring this whole idea that mass times acceleration equals force. Okay? So we've got the scenario, right? Car dies, got to push it. Car has a mass. Notice I've used M for mass, and I put a little subscript, CAR, so the mass of the car. 1,500 kilograms. In this case, we're going to take friction out of the problem. I know, we all know in real life it's there. If you're like me, you've had to push a dead car, and friction is definitely there. So we're told we got a mass of the car. We're told its acceleration is 0.03 meters per second squared, headed east. And it's important that I say east because acceleration is a vector, and I have to have the number and the direction for a vector. So here's the question. How much force is there? Well, guess what? We got Mr. Newton's second law. We can get the force. We just take the mass, 1,500 kilograms, times the acceleration, 0.03 meters per second squared. Bang on the calculator. And it comes out as 45 newtons headed east.
Yeah, I was trying to do this problem, and I was like, all right, Jesus, I'm ready. Take me now.
Okay. Well, I don't know. Does this help at all? Does it, get a little less foggy?
Yeah, I honestly, when I was doing the questions, I wanted to put a little note on the bottom because I had to cheat a little bit just to understand what I was doing. So I went to the actual notes where they gave the answers, and I looked at how they did the problem, and then I tried to replicate how they did the problem so I understood what I was doing, because it was like, for me, it's like reading stereo instructions, honestly. I'm like, okay, wait, what? So I tried to be honest, and I was like, okay, well, God, I'm not trying to cheat, but I'm just trying to understand what the heck I'm doing, because, it's so.
Hey, Joe, that's not cheating. And I've purposely done it this way, so that if you do get stuck, and I encourage you, bang your head on it a little bit, and if you get stuck, go back there. Look. I encourage you to do that because I want you to understand it. So no, you're not cheating. But I do ask that, like you did, bang your head on it for a little bit. And if it isn't making sense, then flip back there. Again, because we only get to get together, once a week, right? I'm empowering you to learn. Please go learn. You're doing great. All righty. So then they give us this picture in the textbook. It's figure 10.4. But this time they've included friction. So there's actually more than one force that we have to account for. And that's where that Greek letter sigma comes into play. We're going to add up the forces. But the right-hand side of the picture, they add another force in there. We got the dog. The little dog is trying to help. And so looking at the car, there's three forces acting on the car. Right? We got George leaning into the bumper trying to get it moving forward. We got his dog pulling it forward, but then we've got friction that's resisting both of them. And so in the picture, see where it says total force? That's where we'd put that sigma F. Sum up all the forces. Add them all up. Well, I got two going to the right. I got one going to the left. So we'll call the two going to the right, we'll say those are pluses. We'll call the one going to the left a minus. And that's what's being shown in that blue type. The total force, right? The guy pushing on the bumper to the right. So George is pushing to the right. His dog's pulling to the right. And then friction is acting left, so it gets a minus sign. That's the total force. That total force is going to equal the mass of the car times its acceleration. So that's what that little sigma, that goofy letter in front of the F means. Add up all the forces, set it equal to mass times acceleration. So Dr. Weil walks us through that, and then he gives us another example, 10.2, to kind of reinforce it. Okay? We got Tony pushing on a huge rock. Rock weighs in at 300 kilograms. Actually, I should say it has a mass of 300 kilograms, right? Which is roughly 660 pounds for those of us that work in pounds. Okay, Tony's pretty strong. He gets this thing moving at 0.12 meters per second squared,
No way.
headed north. Right? And he's done this by applying 300 newtons of force. Go, Tony. Well, the question is, how much friction is Tony having to deal with? All right? So I have found it's very helpful to draw a picture. So we're going to use the big green arrow. That's Tony pushing on it to the right, headed north. But as we learned in friction, friction always opposes motion. Always, 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 always opposes motion. So Tony's pushing the rock north. Friction is acting south. We got Mr. Newton's second law in the picture below Tony. And it says, if I add up the forces, it's going to equal the mass times the acceleration. Well, I got two forces. I got Tony pushing to the right. I got friction to the left. So it kind of looks like this. We'll call Tony going to the right plus. We'll call the friction opposing Tony going left minus. I got friction of Tony going right, F of the man. Force of friction acting left, we'll subtract that. It has to equal the mass of the rock times its acceleration. So we know some of these numbers. We know Tony's pushing with 300 newtons of force. We know the mass is 300 kilograms. We know that Tony's got it moving at 0.12 meters per second squared. So from a math standpoint, if we write it out like I've got down there at the bottom, the only thing we don't know in there is the friction. And with a little bit of algebra, I know. Joe's going, please, no. Don't pull the scab off that wound. It was just starting to heal. We can actually solve that. Turns out friction is 364 newtons. Joseph, how old's your oldest kid?
13 right now.
They doing algebra yet?
No, not quite.
Okay.
But I had to rely on my son to teach me math for the last experiment that we did. He's like, "No, Dad, you're doing it wrong." I was like, "I don't know what I'm doing. Jesus help me."
Okay. All righty. Well, again, force-like acceleration is a vector, so we got a number. We have to give it a direction. All right. And we already figured out since we're pushing north and friction opposes motion, so the friction is acting south. Then he does example 10.3. And you're going to see a pattern here, right? We're going to use Mr. Newton's second law again. But let's look at what they gave us. They gave us the mass of the desk. They gave us A, the acceleration. Oh, there's that two types of friction showing up. We got static with the little F with the little S. And then we got kinetic friction, the little F with the K. Okay, so the question is, we want to get the desk moving. How hard does the man have to push? And then after he's got it moving, how hard does he have to push? Because there are two different scenarios. Remember, we already talked about the fact that you push, and finally it breaks free and gets going. So there are going to be two different numbers. We know that just from our own, experience of living in the universe. Here's the math behind it. All right. So let's do the first part. How much force is going to take to get this desk moving? Well, look at the picture on the right. Okay. Similar to Tony pushing on the rock. Okay. Now I've got Joseph pushing on the desk. And he's got friction. So Joe's pushing on the desk, trying to get it to go to the right. Friction is resisting its opposing motion because friction always opposes motion. Hey, George, in case I was unclear there, friction always opposes motion.
Got it.
Okay. So I got Joe pushing to the right. Friction is opposing his motion to the left. Mathematically, it looks like this. I got the force of the man, Joseph, we'll call right positive, so that's plus. The desk isn't moving yet, so I have to use the static friction. So the F with the little s subscript, static friction. Okay? And I've already answered the question, why F of S? Because it's not moving yet. So at this point, now I can throw the numbers in there. But wait a minute. Wait. I got 0 in for A. It's not moving. So physically, if it's not moving, then whatever Joseph is pushing to the right, friction must be balancing out to the left. And that's what the math shows us. And remember, force is a vector and you have to have a magnitude and a direction. So we said that Joe's pushing the thing, right? East, so therefore, or he's pushing west, so the acceleration has to be to the west, right? Boom. Now let's change it. The thing starts moving. Guess what? Same equation, except look what we're using. We're using the kinetic friction because in this case, it's moving. So there's a difference between when it's moving and when it's not moving. Oh, it's moving. Guess what? It has an acceleration. So we got the force of Joseph, which we called F of the man, right? We were told the friction, the kinetic friction is 110 newtons. So we get a big old minus sign, 110. The mass of the desk is 100 kilograms, and it's going at 1 meters per second squared. Good job, Joe. You got the thing moving. But
If I
notice,
pushed it, trust me, it's gonna move.
all righty. So it only takes 210 newtons to keep it moving. And again, it's a vector, so we got to have a magnitude and a direction. So don't forget the direction. Okay. Boom. All righty. That's Mr. Newton's second law.